Welcome to the video on the squeeze theorem. This will be a two-part video where we're going to talk about the squeeze theorem, and in part 2 we are going to apply it to solve trigonometric limits. So in this first part I want to give you the intuitive feeling of why this theorem is true. So we're going to consider two functions f and g such that one is always below the other, and we're going to say that g is always above. That is, we have this inequality, and we're also going to say that their limits are equal in some point. That is, the limit of f as x approaches a equals the limit of g as x approaches a, and we're going to call that limit L. So let's see how that looks like. Here we have the graph. Here this orange function is function g, and this blue function is function f. And we can see that as x approaches a, both functions approach L. So they have the same limit as x approaches a. And now we're going to introduce a third function that will be this red function, and we're going to call it h. And the function h will be such that it is always between these two functions. That is, its graph is something like this. It is between these two functions. So we can see that as x approaches a, h of x is squeezed between these two functions. And well, in these conditions, what the squeeze theorem says is that the limit of h is also L. And we can see that this result is pretty intuitive, because well, h can't go anywhere else. It is squeezed between these two functions. So as those two functions approach L, h must also approach L. So that's the squeeze theorem. We're not going to prove it here because I don't want to bore you, but the proof is not hard. You only need to apply the epsilon delta definition of limit. So I hope I convince you that the squeeze theorem is pretty intuitive, and in part 2 we're going to apply it to solve trigonometric limits. So see you there.